Welcome to our online tutorial class. This is analytical chemistry from the topic Argentometric titration. And with the Argentometric titration, we have silver as our titrant in the burette, and we are determining also either the concentration of the halide ion, which is in our conical flux. So you put your titrant here, and the conical flux, you have the halide ion, which can be chloride ion, bromide ion, or the iodide ion. So with this titration, there are points that we call equivalence point, in which the moles of the titrant and the moles of the analyte are the same. But before the equivalence point, the moles of the titrant in the conical flux are less compared to the moles of the analyte in the conical flask. But the moment you go past equivalence point, the moles of the analyte in the conical flux start to go down, as the moles of the titrant from the burette is going to go up to have the excess of moles of the titrant. So in this case, we have been given provided with the information for bromide ion. We have 18 and 0.15 as the concentration. So the first thing we need to know that how much of the moles of bromide ions was in the conical flask. So we're going to calculate moles of the bromide ion, which will be the volume that we added, 18.0 times 10 to power minus 3 liters, times, we have to change that into liters, times the concentration, which is 0.15 molar, and that's going to give us 2.7 times 10 to power minus 3. So these are the moles of the bromide ions that we added. And then we're told, after addition of 7.0 ml of silver ions, we also need to calculate the moles of the silver ions that we also added, which is going to be the volume that we added, 7.0 times 10 to power minus 3 liters, times the concentration of the silver ions, which is 0.04 molar, and that's going to give us 2.8 times 10 to power minus 4 moles. So if you compare the moles of the silver ions which went into the conical flask and the moles of the bromide ions which are in the conical flask, you realize that there are more moles of bromide ions compared to silver ions in this case, and therefore we are going to have excess moles of bromide ion. So we are going to say moles of bromide ion in excess. So these are excess moles. So that's going to be the moles of bromide ion, which is 2.7 times 10 to power minus 3, minus the moles of silver ions, which is 2.8 times 10 to power minus 4, so that we know that how many moles of bromide ions did not react with the moles of silver ions. So that will give us a total number of moles of 2.42, will give us total moles of 2.42 times 10 to power minus 3 moles. So these are the moles of the bromide ions that did not react with the silver ions. So for us to get the concentration of bromide ion in part A, we are going to divide these excess moles of bromide ion with the total volume in the conical flux. Remember, we had 18 and then now we have added 7, so it's going to be a total of 25 mils. So we're going to divide this number of moles divided by the total number of volume that we have now, and that's going to give us, so we divide by 25.0 times 10 to power minus 3 liters, and that's going to give us a total of 0.0968 molar. So this is the concentration of bromide ion after the addition of 7.0 mils of silver ions. So this is part A. Let's look for part B after addition of 72 mils of silver ions. So now, do you think bromide ion is still going to be excess, or in this case silver ion is going to be excess? Let's calculate. So after addition of 72 mils of silver ions, we are going to calculate the number of moles of silver ions. In this case, we are going to have the volume that we added, 72.0 times 10 to power minus 3, still times the concentration, which is 0.04. Concentration has still remained the same, and that's going to give us a total number of moles of 2.88 2.88 times 10 to power minus 3 moles. So these are the moles of silver ions that are now in the solution after the addition of 72 mils. So now if you compare with the initial moles of the bromide ions in the solution, you realize that these excess moles, there are more moles of silver ions in the solution compared to moles of bromide ions in the solution, and therefore in this case now silver is the one in excess. So we are going to say moles of silver in excess, and that's going to be the new moles of silver, 2.88 times 10 to power minus 3 minus the initial moles of bromide ions, which is 2.7 times 10 to power minus 3, and that's going to give us a total number of moles of 1.8 times 10 to power minus 4, 1.8 times 10 to power minus 4 moles. So this is now the new moles, the excess moles of silver ions. From there we can calculate the concentration of silver ions, which will be the excess moles 1,8 times 10 to power minus 4 divided with the total volume. The total volume now is 72 that we have added plus the 18 that was there initially, and that's going to give us 90, total volume of 90 that now we have in the solution. And we're going to divide that by 90. We change this into liters because concentration is moles per liter, and this is going to give us 2,0 times 10 to power minus 3 molar. So this is the concentration of the silver ions after we have added 72 mils. But the question, remember, is saying determine the concentration of bromide ion. So to determine the concentration of the bromide ion, we are going to use the KSP that we have been given. And remember, KSP in this case is the concentration of silver ions times the concentration of the bromide ion. We have the concentration of the silver ions, which is this one, and we have the KSP which has been provided, and therefore the concentration of bromide ion will be KSP divided by the concentration of the silver ion. And if we plug this this side, the concentration of bromide ion then will be KSP, which is 5,0 times 10 to power minus 13. This one is given divided by the concentration, which is 2.0 times 10 to power minus 3. So we're going to divide that 5.0 times 10 to power minus 3. We divide that by our answer, and we're going to get the concentration of our silver ion, the concentration of our bromide ion to be 2.5 times 10 to power minus 10 molar. So that's the concentration of bromide ion. Part C is saying that we calculate. In part C, we are told to calculate the concentrations at equivalence point. So remember, at equivalence point, our KSP value, let me do it here, part C. So part C, our KSP is equal to the concentration of silver ion and the concentration of bromide ion. So at KSP, their moles are equal, they have the same number of volumes, so the concentration is the same. So we're going to say then KSP, if we assume that the concentration of silver ion is X times the concentration of bromide ion, which is X. So this is like saying KSP is equal to X squared, and therefore to get the value of X will be the square root of the KSP value. So that will make us to have the concentration of bromide ion, which is the same as the concentration of the silver ions, to be the square root of the KSP, which is 5,0 times 10 to power minus 13, and that's going to give us a value of 7,07 times 10 to power minus 7 molar. So that's how you determine the concentration at equivalence point. You just find the square root of KSP in this case and in this scenario. So let's look at the second one. Calculate the PAG of solution made by mixing 45 ml of that one of silver nitrate solution with 70 ml of 0.45 molar sodium chloride solution. So remember, PAG is equal to the minus log of the concentration of the silver ions. So at any time you are asked to calculate the PAG, the thing that you'll have to look at the end is to look for the concentration of silver ions. So let's look. In this case, we are given the moles of silver ions, the volume and the concentration. So we can look for the moles of silver ions in this case, and we have the volume, which is 45,0 times 10 to power minus 3 times the concentration, which is 0,7, and that's going to give us, so we have 45 times 0,7, and that's going to give us 0,0315 moles of silver ions. And then we are going to determine also the moles of chloride ions. So we're going to look at the moles of chloride ions, which is the volume, that is 70,0 times 10 to power minus 3 times the concentration, which is 0,45 molar, and that's going to give us, so we have that volume, we punch in the calculator, and that's give us 0,0315 moles. So in this case, if we were to write this reaction, we have silver nitrate reacting with sodium chloride, and this is going to give us silver chloride, which is a precipitate, plus sodium nitrate. So you see the ratio of silver chloride to sodium chloride, the ratio is 1:1, and the ratio of silver nitrate and silver chloride is 1:1. But in the solution form, this one is a silver ions in aqueous form, and then we also have the chloride ion in the aqueous form, and this is going to give us silver chloride, which is a white precipitate. So we have silver ions reacting with the chloride ions to give us silver chloride, which is a precipitate. So you can see that the moles of silver ions is 0.0135 moles, and the moles of chloride ions is also 0.0315. So what does this tell you? It tells you that the moles of silver ions and the moles of chloride ions are the same. It means that the chloride ions and the silver ions are in equilibrium. So if they're in equilibrium, so meaning that they are at a point of equivalence, and we are told to determine the PAG. So what we are going to do, we are going to take, because at equivalence point the concentration is the same, so we are going to say then KSP, just like you have seen, is equal to the concentration of silver ions times the concentration of the chloride ion, because it is at equivalence point. And how did we know that? Because these moles are the same, and therefore the concentration of our silver ions here, just like we have seen, we're going to assume is X. So X is going to be the square root of KSP, and that's going to be the square root of 1.82 times 10 to power minus 10. So the value of X, which is the concentration of our ion, in this case is silver ions, will be the square root of that, 1.82 times 10 raised to power minus 10. That's going to give us a value of 1,349 times 10 to power minus 5 molar. This is the concentration of silver ions at equilibrium. But remember, the question is asking you to calculate the PAG, and you have said that PAG of silver is the minus log of the concentration of silver. So we're going to say our PAG is equal to minus log of the concentration of silver ions, and that's going to minus log of 1,349 times 10 to the power minus 5. And if you punch that in the calculator, so just say minus log of answer, that gives us a value of 4,8699, which is going to give us 4,87. Remember, PAG doesn't have units, so this is the value of our PAG. So let's look in this equation. This is from gravimetric method, and the question reads 0.2356 gram sample containing only sodium chloride of this molar mass, and barium chloride yielded that mass of dried silver chloride. Calculate the percent of each halogen in the sample. So you have a sample of 0.2356 gram sample containing. So in your sample, it contains, so this is your samples, and this sample has sodium chloride, and it also has barium chloride. But you are told that after they yielded these two yielded a mass of 0,4637 of dry silver chloride. So you have a sample, and this sample contains sodium chloride and barium chloride, and then when you dry the two, they give you a mass of 0,4637 of silver chloride as the product. Okay, so now we don't know how much, until this moment we don't know how much of the mass was contributed by sodium chloride and how much of the mass was produced by barium chloride. So we need to come up with equations, because we have to come up with the equation to help us understand or calculate how much of the silver came from the sodium chloride and how much of the silver came from the barium chloride. All right, so now let's assume that we can say, now let our X represent the mass of sodium chloride, G is the mass, and our Y to represent the mass of barium chloride. So that's the first thing. So if we add our mass X plus Y, we're going to get the mass of the sample 0,2356. All right, so let's assume now X is the mass of sodium chloride and Y is the mass of barium chloride. So the thing that we need to do is to calculate the moles of silver chloride which came from each. So we're going to start by saying moles of silver chloride from sodium chloride. And if you check, the ratio between sodium chloride and silver chloride is 1:1. So that one will be the X gram of sodium chloride times 1 mole of sodium chloride divided by the molar mass of sodium chloride is 58. So we're just going to write 58,44 gram, because the mole is the one on top, times, if you look, the mole ratio between silver chloride and sodium chloride is 1:1. So times 1 mole of silver chloride over 1 mole of sodium chloride. So from here, this can cancel each other. Gram of sodium chloride can cancel the gram of sodium chloride, and therefore we are going to have the X times 1 mole over 58.44, which is the gram of sodium chloride, and that's going to give us, so let's divide that. Which is going to give us 0,0171111x mole of silver chloride. So the same, once we have this, we're going to get the mass of silver chloride from sodium chloride. So meaning we're going to multiply, and let's just write, then we're going to say mass of silver chloride from sodium chloride, and that's going to be the moles of silver chloride that you have got 0,01711 times x mole times the molar mass. So now we come to use the molar mass of silver chloride, which is 143.32 gram per mole, and this mole will cancel mole, and we're going to have the mass of silver chloride times 143.32, and that's going to give us 2.45, 2.4524 gram. So these are x gram of silver chloride. So these are the amount of the mass of silver chloride which came from sodium chloride, x, because x here represents sodium chloride. So once we have reached here, we are still going to do the same for the part of barium chloride. So we're going to say moles of silver chloride from barium chloride. But this time round, check silver chloride and barium chloride. For each formula unit of barium chloride, you're gonna get 2 moles of chloride ions, which is like silver chloride. So still gonna say Y, because Y represented barium chloride. So Y gram of barium chloride times 1 mole of barium chloride divided by the molar mass of barium chloride is given to be 208 divided by 208,23 gram barium chloride times 2 mole of silver chloride. Why 2 mole of silver chloride? Because for the formula unit we have 1 barium chloride versus silver chloride. So you can see for every 1 formula unit of barium chloride we have 2 chloride ions, and if we were to do it this way, we're gonna see for 1 is to 2, so we're gonna have 2 chloride, and we have silver chloride, 2 chloride, so this is gonna give us 2 for every unit of 1. So we divide this by 1 mole of barium chloride. So this one will cancel this, gram of silver chloride cancel gram of silver chloride, and then we're going to remain with 2 divided by the molar mass of that, 208.23, and that's going to give us 0,009604,604. We can then calculate the mass of silver chloride from barium chloride, and we are going to multiply this number of moles times the molar mass of silver chloride times 143.32, and that's going to give us a mass of silver chloride from barium chloride, which is 1,3765 Y gram of silver chloride. And remember, we are told that sodium chloride and barium chloride gave us a total mass of 0.4637. So we can then say that the mass that we got here, 2,4524 x gram of silver chloride plus 1,3765 y gram of silver chloride is equal to this mass that it produced, 0,4637 gram. So this gram of silver chloride can cancel gram of silver chloride, and let me 2.4524x plus 1,376565y is equal to 0,4637. So this is the same as saying we can rewrite it, and remember our initial equation that we wrote, we had x plus y is equal to 0,2356, because we said let x be the mass of sodium chloride and y be the mass of barium chloride, and if we add the two masses we get this mass of the sample. So with this equation, we can write it as y is equal to 0,2356 minus x. So let's call this our equation 1, this is our equation 2, and this is our equation 3. And therefore, we can write this equation, we can write equation 1, we can rewrite or rearrange equation 1 and equation 3 in this way: 2,4524x plus 1.3765y. But now, instead of writing y, this is our new value of y, so we're going to substitute it and say 0,2356 minus x is equal to this value here, 0,4637. So from here we can proceed and say 2,4524x plus, so we're going to multiply whatever is in bracket times 0.2, we're going to multiply 1.3765 times 0.23, 0,2356, and that's going to give us plus 0.2, 0.3243 minus 1.3765x is equal to, let me wrap this, is equal to 0,4637, and we can rearrange this by saying 2,4524x minus 1.3765x is equal to 0,4637. Because this is a positive, if it crosses the equal sign, it's going to be minus 0,3243. Now, when we subtract these two, we're going to get 2. And that's going to give us 1,075959x is equal to, the difference between the right hand side is going to give us 0,139494. And to get the value of x, we're going to divide both sides by 1,0759. 1,0759. This one cancel each other, and x is going to be, give us a mass of 0,12956 gram. So this is the gram. From all the way where we started from until now, we have managed to calculate the value of x. And remember, x represented the mass of sodium chloride. So it means that the mass of sodium chloride from here that contributed to, the mass of sodium chloride that contributed to 0.4637 of silver chloride is this mass here, 0.12956 gram. So since our sodium chloride, we can just write it sodium chloride, and then because we are told to calculate the percentage, and therefore percentage sodium chloride will be the mass of the sample, the mass of sodium chloride that you have got. Yeah, there's a lot that you have spoken. 0.12956 gram divided by the mass of the sample, which is 0,2356 gram times 100. So gram cancel gram, and that's going to give us, so this mass divided by 0.2356 times 100, and that's give us 54.99, which we can round off to 55%. So the percentage of sodium chloride is this one, 55%. So to get the percentage of, because we have told halogen, and halogen here is chloride, but it was in form of sodium chloride and barium chloride. So to get the percentage of barium chloride, you can just say percentage of barium chloride will be 100% minus 55%, and that's gonna be, so 100 minus answer, and that's gonna give you 45%. So this is the percentage of barium chloride that remain. You don't need to go and look again like for example here we have got the mass of sodium chloride. You don't need to go and look for the mass of barium chloride, you know, for you to get the percentage of barium chloride. Once you have the mass of the percentage of sodium chloride, then because there are only 2 in the sample, it means that the remaining part is the percentage of barium chloride, because a whole gram or a whole sample had 100%. So that's how we approach these questions. Yeah, thank you so much for watching. Hey, remember to subscribe, like the video, and share with a friend so that when we make new videos you get updated. Thank you so much. Bye bye.